Okay, good morning, all of you. Can you hear me all right and see the screen?
Good morning, Professor. Yes, we can.
Okay, very well. So we can get started. So, so far, what we have been doing in the first two lectures was basically setting up a neural network model to learn simple tasks to feature extraction tasks along with some downstream tasks. So we started viewing our hypothesis as a nonlinear function, which is parameterized, or in other words, determined by the weights and biases of the neural network. And then what we did was we tried to learn these parameters based on the task at hand, which could be, for example, as simple as regression or classification, to more complicated tasks like putting a bounding box, etc., which also form kind of a regression problem. Now, what we have seen in the last lecture is that whenever we have images or any structured data, then there is room for reducing the number of parameters. Particularly, recollect the example that I gave when we had this 13 megapixel image, three channels. Then things were slightly more complicated in terms of the number of parameters that one has to train. So, in order to decouple the size of the input to the number of parameters, we started looking how can we decouple that and what are the things that we can exploit from the data. And towards that end, we started discussing what is convolutions and some of the handles that are involved in convolutions, particularly the padding and striding, to control how fast or how deep we can go when we are composing many nonlinear functions. Okay, so but in all these, so far, tabular data or structured data, which could be images or one-dimensional structured data, always we are looking at a fixed window, right? So fixed window, let me know if the audio is okay.
It is clear.
Okay, Sophia, probably it's at your end. So, so far, we have been looking at data that is of fixed window, right? So you give me, say, P features, or it could be an image, say, which is, say, NH times NW. All these are fixed patches of data, right? And within this patch, we did exploit convolution and structure to reduce the number of parameters. But now, today, the focus will be on the following. Imagine that I have streaming data. Okay, so instead of this fixed set of P features, I have P features which would evolve over time. So this is time is equal to 1, T is equal to 2, and so on. T is equal to N. Okay, so now the challenge is whenever we have such streaming data or sequence data, like sequences me speaking, right? So I can go on for like an hour and a half or maybe 3 hours. You never know when I'm going to end, right? So at least in this setting, we know we are going to end at some point. But whenever we are dealing with data, we don't know what is the end of the sequence. Now, imagine what we were doing so far with MLP. So for every P features, we had a W matrix, which was always the at least the input was something that depends on P, right? So it could be, say, we would like to reduce P features to, say, D features, D being the output of the first hidden layer, for instance, the size of the output of the first hidden layer, but the dependence was on P. Even with all this reduction that we did with convolutions, the W that you would eventually learn, the filter size, although it did not depend on the size of the image, it depends on how many such images we get, right? So now the goal of today's lecture is, suppose we have the sequence or streaming data, then how do we control the growth of the parameters? One stupid and naive way is I treat these sequences as independent chunks of data, not exploit anything between what is happening in T1 to what is happening in T2, process them independently, right? Using the same set of W matrices or different set of W matrices. That is one naive way, but often what happens is, whenever we are dealing with sequence data, there is some relation between time instance 1 and time instance 2. So there is something that we can exploit. Now, there is relationship, ordered relationship was there within one patch of data. Now imagine that if I want to learn what is changing from T is 1 to 1 to T is equal to 2, then there needs to be something else that we need to do, along with not letting the number of parameters grow with the number of time snapshots that we get. If I'm dealing with infinite time snapshots, a priori, I cannot basically allocate infinite W matrices, right? So uh, that is not a feasible way to proceed. So towards that end, the main goal of today is something called as recurrent neural networks. There is some kind of a recurrence, and it is particularly suitable for sequence modeling. Okay, so that is the main goal of today's lecture. Okay, but before we do all this, what we will do is we'll do a quick recap from last week on CNNs, and then what I did not go into the details in the last lecture was counting the number of parameters to get a sense of how although I did mention, we did not count the number of parameters, which we will do today. And also what we will do is we will look at one particular architecture called as AlexNet along with a Keras snippet, right? So what changes? And then we will get into the recurrent neural networks. So as usual, what I'll do is I will give kind of a layman introduction to why do we need recurrent neural networks and connect to what humans would do whenever we are dealing with sequences. Suppose we want to process something, we have some information, right? Some information from the past that will certainly help us to process, understand whatever we are dealing with whenever we are telling sequences. So when I'm telling something for 5 minutes, you of course have something in your memory from the past 5 minutes, right? So you would process that in a sequential way, extract or keeping something in the mind of what was the context, right? So that is all we will, that all those things we'll see today. Uh, so we will see what is a recurrent neural network. To do that, we will introduce what is recurrent neuron. We will see how to set up a loss function. How, if once we have the loss function, how would backprop in time work? What are the limitations of that, etc. And then we'll look at some examples and two popular architectures, which are specializations of a vanilla RNN, are LSTM and GRU units. We will see those. Now, what is more recent, again in sequence modeling, many of you might be already aware of this with respect to all these foundational large language models, is something called as transformers. Okay, so transformers is something that we will not cover today, but what we will do is we will look at this particularly when we are dealing with the NLP lecture. So NLP transformers is predominantly popular for NLP tasks. So it is more, it could fit, that module could fit here or there, but we can I think it's also good to break it up into a separate lecture so that we have enough room to discuss these basic aspects. So transformers we will see, but at a later point in time. LSTM and GRU, we will see how we progress in terms of time. If time permits, we'll cover today, or I'll give a basic introduction, but take it up in the next lecture. Okay, that is basically the roadmap for today. Okay, so now let's quickly recollect what we were trying to understand in the last lecture. So whenever we are dealing with structured data, right, these are a fixed window. You might have many such examples, but when I say fixed window, the way you should imagine is I have images, but many images of different buildings, like, or many different images of cartoons, like what we see, but all these are different independent examples. Now, in contrast, whatever story I was telling so far, the way you should connect that is imagine that I have a video. Video is a collection of frames, right? So I put together, say, many videos at certain frame rate. I mean, many pictures at certain frame rate. I get a video. Okay, so that is not a fixed length. Now, when I have to process one frame compared to the next frame, then I have to learn something from the past frame to extract features of the next frame, right? So that is video. So that is evolving with time. And in case of instances, different instances with video, imagine that I have many different videos, right? So for example, like, okay, there's this building. So I take a video of this building, and next example could be video of some other architecture, right? So I have like 100 examples of these Chinese architecture. Some of them are of, say, Hoysala architectures and so on. Those are different buildings. And then these are videos, right? So, but there is some temporal aspect to it, but so far we did not consider, right? So video is more relevant for recurrent, but we are looking at a snapshot of a data of fixed length. Okay, so particularly what we were exploiting is that the nearby pixels are correlated compared to pixels that are slightly far away. And what you basically get is an image which could have multiple channels, right? So all these images will treat it as feature maps, right? So features or feature maps. So you could have multiple feature maps at the input. In contrast to MLPs, first difference is that we don't flatten. We don't flatten the feature maps, right? So what I mean is, imagine that we had this 28 by 28 pixel image of MNest. So that we were not, so MLP, we were converting it to a 784 uh, length vector by flattening it. We are not doing that with CNNs. And second main message is exploit that features are related. Structure. So whenever we say features are related, one simple way to visualize is like, okay, so you have this image, say this could be, say, 12 megapixel image of a building. But now if I simply subsample every 4 pixels and replace with, say, the average value, the message being conveyed in the picture will not change much. Okay, so that means that there is some relation. So maybe simply replacing it with an average is not a good idea. We do with a weighted average, right? That is kind of what we were trying to do here. Now, in order to do all this, what we leveraged as a mathematical tool was this convolution operation, where convolution has two aspects. One is pointwise multiplication plus addition over sliding patches. right? So this is in English, what is convolution, right? So what we do, as we see in this animation, you start with one patch, you do a pointwise sum, you get a new element in the feature map. Okay, so that is what we are doing. Now, there are certain limitations, right? For example, the size of the filter that we use, that is the side of the gray square that is moving, that is the size of the filter or the kernel. Now, this kernel, what we are doing is we are sliding this. Now, whenever the size of the kernel and the size of the picture are not divisible, what I mean is, suppose along with the striding that we use, then what we do is we end up in scenario like this where we have some pixels that overshoot, right? Which means that in order to do a pointwise addition and multiplication of this particular area, we need to do something. And to that end, what we introduced was the second concept is the padding, right? So we add zeros to basically artificially extend the image. So without changing much uh, information wise, no change at all, but it leads to a valid pointwise multiplication. Now, where is parameter sharing happening? If you look at this, the gray tile that is moving, that has certain W's associated with it, certain W's and B's. Okay, so now from one slide to the other, so whenever I'm doing the scanning from one position to the other position, I'm using the same set of W's. So I'm sharing the parameters across the image. And that is what will also lead to the gain in the reduction of parameters and not let the number of parameters grow as the size of the picture grows. Okay, so does it make sense, Rupesh? So we have a gray slide. So that has W1 to W9 in this particular 3x3 case. Now, when I move to the next one, I'm still using the same set of W's. I'm not changing W's. Okay. So what that means is like, it doesn't matter how big the picture is. Since I'm still using a 3x3 filter size, I can do that slide. Now, if the picture is very big, right? So that means that the scan time would increase, but at least the memory is controlled. Okay. So now that was one thing. Now the third concept that we introduced was stride. What is stride? Stride means how fast should I do the scan? Do I do a one hop or a two hop or a three hop? That is the stride length. Why is that required? That is directly reducing the memory size. If I'm moving over this picture very fast, then the size of the feature map would, of course, be reduced because the number of hops you make determines the number of pixels in the feature map. So if I'm moving very fast, then I only have fewer pictures. So what we basically introduced was two knobs. One is to control, both these knobs play the same role of controlling how fast or slow can I change the size of the feature map. Now, the fourth concept, which we also introduced, is the concept of pooling. What does pool mean in English? It is basically collecting information. So, pooling, what is important to note in pooling is there is no learnable parameter. Okay, so there is no learnable parameter. There is nothing to learn there. So pooling, basically what that means is, suppose I have this image. Now, if I use a, so if I have, I'm sliding again with the pooling. So if I'm looking at the pooling of this particular patch, okay, so a 2x2 pooling size. So if I'm looking at this pooling, I can basically do multiple operations. One is I can replace the 4 pixels with the average. That means there is no particular training going on. Or I can replace with a max value, right? So again, this is a non-learnable deterministic operation that we do to reduce the size of the feature map. This could be because with convolution, with all the striding and padding, maybe you are doing kind of oversampling the image, having many more parameters, feature map of very high resolution, which might not be actually required. Now, for a given task, the way it would design the filter coefficients would of course be to maximize the end goal, which could be classification accuracy or regression accuracy. So even with the reduced resolution feature maps, what is the maximum accuracy that we can achieve? That is what the neural network is going to train towards. So pooling is a deterministic operation. There is no learnable parameter as such involved in pooling. You could do a max pooling or a average pooling. Typically, max pooling is widely adopted. Okay. So now what we have as a convolution layer is we have an input layer. This input layer particularly has 3 feature maps. And that is because of the RGB nature, right? So now if you're looking at a remote sensing application or hyperspectral imaging, where you have multiple wavelengths, then you basically have as many of those channels as the inputs given by the sensor data. So now we do all this. Okay, so now this becomes, say, multiple feature maps, right? In this particular example, let's say 64 feature maps. So 3 becomes 64 feature maps, and the feature map size, how do we do that? We compute that based on this formula. We as in we don't have to manually do that, but there is a deterministic relation between the size of the input, the size of the filter, and the size of the feature map. And the 64 might become, say, 128. Okay, what does that mean? We are trying to the feature map, the input output relationship is known to us. What is unknown is what are the filters that we need to use. Okay, this is what we are trying to learn. Okay, and how many of those do we need to learn? It depends on the size of the number of input feature maps, the number of output feature maps, and the size of the filter. Those are the total number of parameters that we would learn. And what we have also seen in the last lecture is that whenever we look at uh, the feature maps in the initial layers, these are more interpretable. Interpretable in the sense that you would get features that are more basic, like straight lines, color maps, uh, colored lines, and so on. But as we go more deeper and deeper in the layers, if you take a dump of what is going on here about the feature maps, this will be more abstract, right? And that is what the network is going to learn, that we cannot basically interpret, right? So that is typical behavior when we train a neural network for whatever task. You can also try to see what are the weights it learns. Does it make any sense, right? So if you do that analysis, you would see that for most of the convolution neural network architectures, the input features are kind of interpretable, but the input and the initial layers, but input is of course the image itself. The output becomes as we go towards the output, it becomes less and less interpretable. Okay. Okay, so is there any calculation for stride with respect to pixel? What is the size of the filter and the so the parameters remain same per feature map. Okay, the parameters are not changing. You learn the parameters. The parameters, of course, will change with respect to the number of epochs as we train. So in the next picture, I'll elaborate on this. But when we stride, what happens is the size of the feature map changes. Okay, so when the size of the feature map changes, it puts a load on the GPU because you have to store as many feature maps as well in the GPU, right? So imagine that when we are doing this backprop computation, we did a small exercise where we were computing what are the matrices and the vectors that we need to store in order to compute the output feature. So now imagine that, okay, I have 64 feature maps of whatever size. Now, in order to compute the gradients, etc., I will have to store those 64 feature maps of whatever size it is. Now, if I'm using a very small stride, the size of the feature map increases. That puts a load on the memory. Okay. And the size of the filter, of course, determines how many parameters we need to learn. So that basically increases the number of parameters.
Professor, one request. Can you explain pooling one more time?
Yes, I will do that.
Thanks.
I'm going taking questions one by one. So is there any calculation for stride with respect to number of pixels? So what is deterministic is basically the output size. But what stride we need to pick for a particular image, that's a hyperparameter. There's no formula to compute, okay, if I have this particular image, I need to use this stride. So that is kind of comes with experience, or you basically play around with multiple stride parameters to see if I can still get the same accuracy. So in other words, what I mean is, suppose you fix a stride of length 1, and for a particular task, stride 1 uniformly across all the layers, you pick that. Now you get a certain accuracy. Now you can change the stride to, for example, 2, which will reduce the memory consumption, as I mentioned, but the accuracy would not drop too much. So, which means that if you can leave with that little drop in the accuracy or no change in the accuracy, but gain in terms of the memory, you can go with the higher stride. Okay, but also as I was telling in the last lecture, so suppose like I'm dealing with some bounding box of images like say landscapes or beaches where nothing much is changing. So then you can already start with a higher stride length. So all the inputs and the outputs of a neural network, we call them as feature maps, except that the input is the data, right? So it is the image of this building, which has RGB components. The input is an image, but you can also call it as a feature map. So all the inputs and the outputs of a neural network are features. Why is it called a map? Because we are dealing with 2 dimensions, so you don't call it as a, say, a feature vector, but it is a feature matrix or a feature map. Okay, input and output are of a neural network are always called feature maps. Yeah, so when I say interpretable, when you take a dump of the say the feature, the filters that you learn, you plot that. Okay, then you see that, okay, like what we saw in the discussions in the last lecture was, when I look at this the vertical and the horizontal filters, right? So this is what was the intuition. Now I need to use some basic filters to basically extract all those initial features, right? So that was the understanding, right? Or that was what I used to explain. Now the question is, okay, this is what humans should do. So we will break down the image into some components that are basic building blocks of an image. But are the neural networks also doing the same? We build this neural network under that hypothesis, but when we really see what are the filters that are being learned, so you train all these W's, now you can plot these W's, right? All these 3 by 3 filters, many of those at the initial layers, And if you plot those, you would see indeed that the neural network is also learning those basic curves, basic color maps, etc. Right? So that is when we say it is interpretable. Interpretable in the sense that we can make sense of what is going on. Okay, so this is what the understanding was, and in fact, it is also trying to do the same. But now, if you plot the filters for layers that are towards the output layer, those filters are less interpretable. It will become like more abstract art, right? So it cannot make sense of what is going on in that easily. I'll come to AlexNet. So higher stride will result in lower accuracy. Might might lead to or might not lead to. It depends on the input data, right? So the best thing is to do something called as an ablation study, where you check with different number of strides, different uh, pooling lengths, whether we require padding or not. So basically, you make a table and then you see what is the accuracy that you get with the best set of combinations. Uh, and you will have to do that again for a different problem and a different data set. It doesn't mean that, okay, for one data set, I choose a particular set of these hyperparameters. It need not work the same if you change the task or if you change the problem. Okay. Okay, Jayanti will do the computation in the next slide. How the weights and biases of the convolution are being learned. I'll explain that. So I think I took more or less all the questions. Piyush, you seem to have something. Yeah, go ahead.
Yeah, so very fundamental question. Still don't understand how this works. So we've got a 3x3 filter. We're scanning the image in strides, and we're analyzing each of them. So suppose it's a grayscale image. So there's only one feature map that we have to deal with at the input layer. We analyze the image, we set up some parameters, and then we take a stride, take the next part of the image, and we try to update. Or do we store them differently, or do we reuse the same parameters and store different values?
I'll explain that with yeah, in 2 slides again.
Okay, all right, thank you.
Okay, so let's continue. So now okay, so pooling again. What is pooling? So suppose at this point, I got feature maps. Okay, so now this feature map would be of size, say X by Y, right? So just to keep it a bit more general. So with whatever operations filter size that you choose, you get an X by Y feature map. Now, this X by Y feature map that we get after this convolution layer could be of very high resolution, right? So very high resolution in the sense that even if I subsample the feature map, I might not lose much information. Or for memory purposes, I would like to subsample that feature map. I would not like to store this large feature map for every layer. So now pooling is, in other words, subsampling. Subsampling would always mean that you pick one out of, say, k out of n pixels. That is subsampling, right? So you would just basically arbitrarily pick, or with a rule, you pick a few out of many samples. That is subsampling. Pooling is a type of subsampling, but you need not always choose k out of n, but you can replace, say, with max of 1, 2, 3, 4. This is also leading to the same goal of reducing the size of the feature map, or you could replace with the average of 1, 2, 3, 4. Okay, so not just like picking 1 or 2 or 3 or 4, which is subsampling, but now if you do this, then you get with one more feature map, which is with the average, right? So, or a max, right? So that is pooling. Now, the only goal of pooling is that now I have a larger pixel size or of the feature map after convolution. Now, what you're basically doing is you're reducing it. Okay, so now what you're challenging the neural network is to learn to make sure that it learns all the filters, even with this low resolution processed feature map after pooling. Okay, so that is what we need to keep in mind. Now, uh, typically, what I also mentioned is you have an input layer, you have a convolution pooling, and then eventually what you're basically doing with all this is extracting features. Okay. Now you need to do something with that feature, right? You need to do an inference, and this inference is basically done using a multi-layer perceptron. At this point, you flatten. Okay, so you flatten the feature map at the last layer, and then you have the multi-layer perceptrons, which are basically the affine combination, affine transformation and non-linearity. And eventually you get your estimate of the label. So now what you do is you have your data and your mini batch. You set up a loss function to bring the label close to the hypothesis. You do this over all the examples in the mini batch. Now, what does this depend on? This is a function of the weights and biases, weights and biases, weights and biases, weights, biases of all these layers, right? So those are the unknowns that you would figure out. So what are the weights and biases in this case? These are the filters or the kernels. Okay, so these are the weights of the neural networks. Okay, so these are all the unknowns that we would learn. So again, instead of directly giving a tabular data, we are extracting features using convolutions. Okay, and then once I have extracted features after many layers, you use those features to make inference. This could be, for example, a bounding box, a segmentation, etc. Right? So that is what we are doing. Now, it is typical that you put a convolution pooling, etc., to make an inference, like what I was also telling. Now, what changes in all these popular architectures that you see, right? There is nothing complicated going on between these architectures. Every year, there used to be something called as an ImageNet challenge. ImageNet challenge is basically a set of images that have been uploaded somewhere. Like, okay, it could be like pictures of faces to begin with, or some more complicated image classification tasks where there's a squirrel, uh, just a squirrel, there's a squirrel with many animals, there's a squirrel with some other background, etc. Now, the goal is to basically classify. And the consequence of this challenge was basically these architectures. So every year there is a leaderboard for the image. The as time progressed, the images got more complicated, right? So before it was like the pedagogical ones, right? Handwritten MNIST digits, or just a face that is uh, uh, kind of pre-processed without any background, etc. So those were the initial image databases. As time progressed, people started to challenge these neural networks with different, more complicated images. All these architectures are consequence of these challenges, and they were the leaderboards, top in the leaderboards in the ImageNet challenge every year. What changed from one architecture to the other? The only thing that changed is how many filters we need to pick. Do I need to pick a 3x3 filter or an 8x8 filter? Do I need to put uh, convolution pooling, or do I need to put convolution, and then pooling? right? So these are the things, basically mixing and matching the three basic concepts that I mentioned. We will see one such architecture as we progress, along with some other engineering tricks, for example, that the AlexNet did, right? So, but the remaining ones are kind of um, uh, at at that point, still they are important, but there is nothing more educational there. It is tweaking the parameters, right, to see what is the best that I throw to get the best accuracy. Now, what does it mean for us when, and for example, like Google Net, uh, you can imagine the servers they put and the number of data they throw, the size of the models that they can afford, even back in the times. But what does it mean for us? I already mentioned this in the previous lecture, but what is the use of that? For example, imagine that you are looking at, say, face recognition task, and then your goal is now to detect somebody with a eyeglass or not. Right? So if somebody is wearing the specs or not, right? If that is a goal, then the question is, how do we make best use of the existing architectures for this particular task? Back in the days of pandemic, it was very common to have these problems where you detect a person with mask or not, right? So even for most of the face recognition based locking of the phones, it nowadays allows detection even with a face mask on, right? So I don't know with Android, but at least with the iOS, you can basically wear your face mask. Now it's not relevant anymore, but 2 years back, if you see, that was kind of important because of the pandemic and around. Uh, so now you have spent a lot of resources to get the best model with by training with all these many of examples that you have. Now the question is, can I leverage these models built by Google, etc., to do this little task that I have to basically detect a person is wearing a glass or not, right? So that's a simple task for whatever reason you want to do, or you would like to build a face recognition system with even a person having a mask, right? So now face recognition has been done, right? So with Google Net or AlexNet, for example. Now, for us, we might not have many examples with people wearing glasses or not. We might have a limited set of parameters, a limited set of images, which means that I cannot train such a big network with these limited set of images. Now, to do that, what is commonly done is something called as a pre-training procedure. This is even more common nowadays in the context of LLMs, where clearly there is no way that we can crawl the entire web like what Meta and Google does, but we can still leverage those LLM models to do whatever little tasks we have building a chat bot, etc. Right? So those are possible. And central to all that is a procedure called pre-training. Although I tell this with an imaging example, but you can basically generalize this to any setting or any neural network model that you can think of. So it has been designed, a deep neural network has been designed for a task A. Now, that is with respect to face recognition that we have. Now, suppose I have a new task at hand. What I can do is I can take those initial layers or the models from the AlexNet, and then the last layers were basically designed to get better accuracy for AlexNet or the ImageNet challenge. Now we have a different challenge for us. Now what you can do is you can reuse that network and pad additional layers. For example, have one or two additional layers, maybe an additional MLP layer and maybe an additional convolution layer. And you train only those layers where you, while keeping the initial weights and biases as fixed, which means that when you're computing the gradient with respect to the loss function, you only learn the parameters of this additional layer that you have. Okay. So, which means that whenever you have limited data, in contrast to number of unknowns that you might have when you're training all these layers, the number of unknowns that you have only due to the last layer is much smaller. Okay, so that means that I can still hope for something because I have fewer parameters to train and fewer limited training data. So you only vary those parameters. Okay, so that is something called pre-training, and a simple way is you can go to many uh, um, uh, pages like Hugging Face, or there are many repositories where you can basically simply download the model. And when you download the model, what you get is basically the weights and biases. So now, and the architecture, of course, now you can basically do small changes to incorporate the initial base model and then continue further with your training. So this is called pre-training, a very important procedure, not limited to images, as I mentioned, but you could use it for many other tasks. So now, what I've done here is I've taken we saw this image previously, but it was animation, right? So now I have taken one particular snapshot of that to again go through what is changing, right? So that was related to a question. So let's take a look at the convolution for the first layer, where you have 3 input feature maps. Okay. 3 input feature maps. So these are coming from RGB, for instance. Okay. So now our goal is to get 2 output feature maps. Okay. And then what you say is, I would use kernel or filter of size 3 by 3. Okay. So these are the things that you specify. You tell how many outputs you want, how many inputs is already kind of known to us. Now, the question is, what will be the number of parameters that we train? Now, as I was also mentioning in the last lecture, is the following. The size of the filter or size of the parameters in the filter is the following. It depends on the size of the kernel. So this is 3 by 3. Okay. And it depends on how many input feature maps we have. Okay. So what that means is, for every input feature map, I get one filter. Okay. So for R channel, G channel, and B channel, I get one filter, R, G, and B. Okay. So that is the number of inputs. It also depends on how many such feature maps we have. So this is corresponding to output 1. This is corresponding to output 2. Okay. So plus you have a bias, which is 1, and this is as many number of outputs. So this is filter size. This is input feature map. This is output feature map. This is output feature map. Okay. So now you sum all these. So for this simple going from 3 input to 2 output feature maps, these are the number of parameters that we have to learn. So in this case, you have 9 times 3 times 2 plus 2, right? So you do this math, whatever it comes out to. So that is the total number of parameters that we are learning. These are our unknowns, right? So these are the number of unknowns. Okay. So now when you are computing the gradient, right? Setting up a loss function like what we were discussing here. Now this loss function is set with respect to all these parameters, right? So this is unknown, like all the entries in this. All we fix is, like I say, 3 by 3, but now what is going on in this 3 by 3 is unknown. And that is what we learn during backpropagation. Okay. So for any particular task, again, what you're doing is the following, right? So it doesn't matter what task is, you would have many convolution layers. Okay. What we discussed here is the number of parameters that we learn as a consequence of the convolution layers. Now, you flatten and then you do MLPs, which will also have more parameters that we have to learn. All these parameters are learned using gradient descent backpropagation. Now, the task, what is changing from one task to the other? How is this WB changing from one task to the other? That is based on the loss function that we set up. For example, if you want to do object detection, right? So you want to basically detect an object, what you would do is your training data. Suppose, okay, so I have this person, okay, in the image and along with many other things. Now, what your training data would basically contain is, it will contain many images like of this Waldo, and then it will also, for example, it could be like an S-no type thing, right? So now if 100 images examples, and you might have a label 10, which basically corresponds that, okay, anywhere in this image there is Waldo, I give a label of 1. If there's no Waldo, I'll give a label of 0. You have thousands of such images. Now your loss function is basically based on these training data. If your task is now to put a bounding box, now you just don't give a 1 or 0. You would basically say that, okay, what are the coordinates, right, of this and the size of the bounding box? That is what goes as your label. So that is what you. Okay. So now redoing this for this slide has two messages that you should take home. One is the computation of the number of parameters. You don't have to manually do it. Like you do a model summary, you get this. So how do you code it? As simple as what we did for the dense layer. So what you basically do is a set of convolution max pooling, and so on. And then at some point you do flattening. Okay, so flattening you do, and then you basically get a soft max at the end. So this is basically done for fashion MNIST. Now, what we will do is, there's nothing more to say about this, but what we'll do in this particular case is see what are the parameters. So now, in this particular case, what we have is a feature map at the input, and the filter size is 7 by 7. So the number of parameters that we get is basically the size of the output that we get, 64, times 7 by 7 for one image, right? So this is a grayscale image, so there's only one channel. So that is the input is 1. So 64 times 7 times 7 plus 64 for the bias, you get 3200. Now in the next layer, we want 128 output feature maps. And we are using a 3 by 3 filter. So this is the size of the filter, size of the number of feature maps, 64 from the previous layer, 128 from the output that we desire, times 3 by 3 filter size, and 128 for biases for each output. That is going to give you this particular number. Okay, so this is just for your information that you have to know how these numbers are coming, but you do a model summary, you're going to get these lists. So as I already was mentioning during MLP training, that suppose now we do this pre-training procedure and I say, train only these parameters. So you basically you can set the parameters as fixed and only train a few parameters. So that would basically mean that all these, say, except for the last one, all these are kind of fixed. The number of trainable parameters will only be this many in those cases. Okay. So now, this is a simple example where you see that you can key in the size of the filter, you can key in the number of output feature maps, and then finally you can tell what is the padding required, activation function required, and so on. Now, the question is how to choose the size of the filter, how to choose the number of feature maps that is desired, and anything else, right? So all these parameters, how do you choose? The general answer to that is the following. Although the specific number, there is no, as I said, these are outcomes of many challenges. There's no particular formula with which you can compute, okay, AlexNet uses 96 for some reason. It is based on tweaking to see what trial and error, to see what gives you the best accuracy for that particular challenge. So this one is like a challenge from 2012, right? So that was the best performing neural network architecture. So the general answer is the following. So initially, what we have is an image which is informative, but we also know that the images that we deal with is not noise. Okay, so that means that what I can do is I can basically use filters that are large, which means that the gray tile that we use to scan, these are larger ones, right? So if you see this, the filter size is shrinking. So you start with 11 by 11 and then become smaller and smaller. So I can use a larger filter, but I use many of those filters, right? So 96, so you basically use filters to extract basic features. Okay, so and an image might not have too many basic features, right? So how many straight lines and curved lines you can think of? So what you use is in the initial layers, larger filter sizes, and you would have fewer feature maps. Okay, because again, feature maps, horizontal and vertical filters, there are not many of those, right? Now, as we go deeper and deeper in the architecture, what we do is we reduce the size of the filter because you would like to go through those feature maps carefully with a smaller filter, not a larger one, a smaller one, go through that. And you start increasing the number of feature maps because you want to extract more and more abstract features, right? So this is the general notion. Why 384? Why not 400? There's no answer to that particular question. So generally, the prescription is the following. You would use fewer feature maps, larger filters in the initial layers. As we progress, you reduce the size of the filter, right? So you would reduce the size of the filter, so 5 by 5, 3 by 3, and so on. And then you would increase the size of the feature map, okay? Now, that is a general prescription. Now, in this particular case, you see that, okay, yeah, 384, and then they drop it again. That is no particular answer to that, but that is the general prescription. So initial layers, you use larger filters. And then as we progress, you use smaller filters. Okay, I mean, as you progress, you use smaller filters, but larger feature maps. That is the general prescription. Now, oftentimes, what happens is that you might not have enough, and this is one other major development that happened along with this AlexNet was the use of augmentation. So ImageNet, the challenge organizers gave about, say, 100,000 images, right? So now, can I generate more images from what was given to us? And why is that required? Because if I have more data, then I can train a lot more parameters in an efficient way. Efficient way in the sense that it performs better. So towards that end, what was done in ImageNet was the following. So for example, like if you have this particular image from class 1, which is a particular type of a flower or a mushroom, whatever this is. So what was done was to artificially generate more images from that particular class. So starting from this one image, you see that you are generating 6 more images. Now, what is changing from one image to the other is that now you're basically using, say, different rotations, illumination, etc., to generate new training instances. Okay, so you crop an image, you basically pre-process, extract what is required for that image, flip, rotate, right? So these are different augmentations. Introduce a blur or a noise in the image so that it is also robust to that. So basically, whatever manipulations you can think of, it is going to generate more images from class 1, from the same class. So it's like multi-fold increase in the number of data samples through a deterministic set of operations, but it might not always lead to a better accuracy, but certainly will not worsen the accuracy, right? So that is the philosophy. And this was one of the things that was introduced in the LXNet, which is data augmentation, which is kind of now more or less a standard procedure that is followed in any neural network model, right? So wherever you can generate artificially, by artificially changing a few things to generate more images. Okay. So why two output maps? So this was just for computation purpose, right? So in practice, as I was telling, you would use these many feature maps, right? So you start with say one image and then you want to generate 96 images or 384 images and so on. Okay. So that was AlexNet. Okay. So now to summarize everything that we have seen so far, we started with unstructured tabular data to begin with. And then we started looking at structured data. Structured data, again, this could be, for example, a time series data, right? So you oversample, but you're looking at a fixed window. Within this, there could be a structure. So what you can basically do is you can do a 1D convolution to basically look at small segments, extract feature maps out of this, right? So you basically generate a smaller feature map, right? Or a signal out of this 1D data as well. So for tabular data, you would use MLPs. For structured data, predominantly vision-based applications, you would use convolution neural network architectures. Now, what we would do in the subsequent portion of the lecture is how do we deal with sequence data? Sequence data could be structured. It can have some relation from one time instance to the other. Again, the way you should look at this is, I can have a time series of structured data. I can have a time series of unstructured data, right? So what the time series of structured data would mean that I have a video, which is a collection of several image frames. Time series of unstructured data could be, for example, like you have simply stock market data, right? So with features, right? So but that is varying with time, and I have multiple such multivariate signals. So we have streaming data of images, right? So, or tabular data. Now, what is the architecture that we should look into? right? So CNN was done. Now, what is that? So I have x of t going from 1 to, I don't know, it can go to, it can end at some point, not known. For example, like, yeah, the speed signal that we illustrate here. Now, what are the tasks that you would like to do? You would like to predict, right? So your output, say at time 2, could be, for example, the input that you will expect at time 3. So in this particular case, you do some processing, you should do a one step ahead prediction. For example, you would process time at this point, and the output that you expect here, output of the network, could be, for example, you, right? So that is a prediction task. Okay, so you would process this sequence and to do a prediction, right? So to see what comes next. That is what we will discuss as we progress. Okay, so that is what we will do now. So before we proceed further, let me see if I answered most of the questions. Related to the mini project, we will take this discussion maybe outside the lecture or during the break. But apart from that, is there any question specific to CNN, etc., that we covered so far before I move on to the next change gears and move on?
Professor,
Yes,
I have a
go ahead.
question. In the number of, basically the number of outputs in each CNN layer is determined by what we are passing in the con2D, the first parameter, number of outputs, as well as one of the dimensions of the filter. Do we also uh, tune those as part of hyperparameter tuning, or is it okay?
Yeah. So the number of outputs, a small correction, number of outputs is not determined, right? So it is an input that you give.
Yes, yeah.
Right. And as I said, the general prescription is the so as I was telling, so whenever we are there in the initial layers, right, what are the features that you expect in the initial layers? So these are like the basic aspects of an image, like straight lines, curves, color maps. There are not many of those, right? So you look at any of the many different classes of images, those basic feature maps are more or less the same,
Yeah.
right? So, but it could be appearing in different combinations or different varieties, but the total number of those are kind of limited. So the general prescription, as I was telling, is that initially you would use fewer feature maps, but you use larger filters. Because if I look at a image, then more of a person, not much is changing, right? So like, okay, there's a face, there is etc. That okay, that's why you could use larger filter sizes. So 11 by 11, 96 of those.
Yeah.
Now, as we go deeper and deeper, the features become more abstract.
Yes.
I need many of those abstract features. So that's why you start increasing the number of output feature maps. So for example, you go all the way from 96 to 256, right? So 256 again becomes 384. But at that point, since you would like to focus on a smaller patch compared
Yes.
to what you would do with the initial one, so there you start reducing the size of the filter.
Okay.
Okay, see, ideally, what I would like to want to do, if I have infinite memory, I would like to have infinite number of feature maps and infinite number of filters of infinite size. That is not practical
Yes.
because it consumes a lot of memory. So now what is the best trade-off given the nature of images that we are dealing? So this is the prescription.
And do we also tune these 11 by 11, 96, 256, etc.? Do we tune these as part of hyperparameter tuning?
Yes. So for example, like you see, there is a slight deviation going on here from what I mentioned. So all of a sudden, like 384 becomes 256,
Yes, yes.
right? So ideally, by my prescription, 384 should become like some 500 something. Now, how would you figure this out. So you would start with the prescription 96, 250, 96, 256, 384, and 500. But then once you get, say, whatever accuracy that you are desiring, right? So, okay, you would want like, say, 95% accuracy on your training and validation data.
Yeah.
Now you start questioning. So, do I really require those 500? Can I try to achieve the same accuracy with, say, 400?
Yes.
So that's part of the tuning, right? So
Oh.
initially you start with a certain set of parameters and then see why do you want to do that? So why not? If I am able to deal with lower memory, why do I need to overstrain?
Yeah.
So that is typical. We call as hyperparameter. So hyperparameter, one thing is like, okay, you don't even know what to start with, right? So in this case, you know the prescription. So you would figure out these numbers, but fine tune those numbers to see if you can still leave with those reduced accuracy numbers.
Okay. And Professor, for hyperparameter tuning, apart from grid search CV and randomized search CV, there were some hyperopt and optuna also we had used in ML. Uh, I mean, those were giving quicker results. I mean, those were giving better results, but those were
So yeah,
running quickly with XG boost, etc. I mean, the gradient boosting ones, but those were running very slow with random forest. So how does it work with neural networks? I mean,
so the see, I mean, the underlying foundation is random search and grid search.
okay,
Okay, now how do you implement those? Those are the things that you are mentioning, right? So people have done like efficient implementation of those. But the basic thing, I mean, basic thing that you can think of, like there are twofold, right? So one is either I go do an exhaustive search over all possible parameters,
yes,
which is of course slower. The other one is like I randomly probe a few points to see what works best. Now, there is a middle ground between these two. So I choose a random set of parameters, but then the next random draw I make,
yeah,
I can do that based on the output that I got in the previous one, right? So, like imagine this exhaustive search versus bisection, and that you might have studied in school, right? So you divide the area into half, you focus on one particular area. So there are different implementations around this. One of them could be more efficient in a particular tool that you would use. But in general, any randomized based methods are much more quicker.
okay,
Yeah. Okay. Yeah, and the say the the same logic can be also used to tune the hyperparameters that we see on the screen.
okay,
So it's not necessary that the hyper see everything that is tunable are hyperparameters,
okay,
and you could either do it by a grid search, or here you would not do an exhaustive grid search in these cases, right? You have many layers, and then okay, I mean, imagine those billion parameters to do a search. So you start with something, and then you would see, okay, can I further get an efficient model?
okay. Thank you, boss.
Okay.
Professor, can you explain the trend for this third column, like where we have 55, 27? So somewhere it's increasing. Yeah, this size, this column here.
The size is basically the computation that you do. So that is kind of determined, right? So you remember this formula that I was giving, right? So this one, so that is the consequence of that.
Okay,
So that's yeah. So that's not basically something that we control.
okay, thanks.
So I saw a raised hand. So was it you, Rajay? I think
Yes, yes, it was
okay.
me on.
Okay.
Profession? Am I
Yes.
audible?
Yes, go ahead.
Uh, just one. Hello?
Yeah, go ahead.
Yeah, sorry, my audio had some issue. So I have some basic queries, but I'll not take up time now. Can we discuss after the class, like after the lecture is over? Is
What
it
we can do is the best is to schedule a slot on Thursday.
okay?
That is one, and if it's immediate consequence that you think might be useful
Yeah.
to others also, then we can do it during the break.
Okay, sure. Yeah. Thank you.
Okay, so with that, let's switch gears and look at this new architecture that we will study today, and that is the recurrent neural network architecture. So recurrent neural network architecture was basically designed again to handle uh, time series data. When I say time series, you need not think of a 1D time series signal, but it could be a sequence, right? So for example, imagine the following, right? So you're typing email on any email console these days. It is already predicting the next word or the next set of words. When you're dealing with, say, weather prediction, you would like to see, okay, this is the weather so far today. How would it look like in the next half of the day? Or suppose you would like to, for instance, predict the variations in the stock market, variations in the sales, right? So the sales, how do my sales look in the next quarter? Okay, so based on whatever was going on in the previous quarters, can I do something? Or given that, okay, in the, say, quarter four of the previous 10 years, this is how the sales were behaving. Now, based on that information, can I predict? So that is the basic question beyond regression and classification that one can think of, right? So now, in whenever we are doing inference, so for that we require a model that does not increase in size along with time, right? So I'm processing data. I don't know, the data might stop, it might come, but I do not want to allocate many parameters for infinite number of time samples that I get. So that is the basic idea behind studying recurrent neural networks. And here I just give two examples that we'll again revisit as we progress. So imagine the following, right? So I have a sequence of these words that are coming. And now what I would like to do is the following. I would like to solve a classification problem here. And the classification problem is to analyze the sequence of this text and to decide whether this movie was hit or a flop. Okay, so for example, you see that this movie was bad and long, etc., blah, blah, blah. And then at some point, you see an end of sequence token. And based on that, you would like to make a prediction whether it is hit or flop. So this is typically called as sentiment analysis. Okay, sentiment analysis is a binary classification problem. And the way this is basically done is the following. So every word is a collection of strings. Now, in order to train a neural network or train any ML model, I need a representation for that. There are many ways to learn representations for words. A simple representation is like, for example, if I say my language has, say, 10,000 words, each of these 10,000 words, I would basically allocate a particular, hash it to a particular number. Okay, that is one way of representing, right? So one number or a vector. Or there are things like bag of words, etc. But without going into much details at this point, so you basically get an embedding, right? So there are ways like bag of words, word to vec, etc., which would convert this into number. And then you process this number using the magic box that we will discuss today. And you start generating things. Now, what you need to keep in mind here is, while you're deciding this, you're not just focusing on the current input, but you're focusing on all the inputs that you have seen all the way up to input 0, because if I have to decide, summarize, do sentiment analysis, I need that prior information. Context should be there. So for such architectures, for such problems, you could use the model that we will discuss today. The other easy to understand option is like you have a time series, whether it could be stock or whether it could be the sales. So you would like to see what comes next, right? Whether the prediction is going to have a positive or a negative slope, as simple as that, or maybe predict the value, or say, for example, like, okay, look at Nifty 50 data and then predict what is going on with, say, Nifty next 50, right? So is there any correlation or any pattern that you can try to infer? So that is the basic idea behind recurrent neural networks. Now, before we end, like what we did in the last class, I will just put a few um, um, images to see how you would react, and then you would explain as usual how you did, and then we will see how that goes. Okay, so now what you see is basically a picture of a ball, right? Now, what I would like you to answer in the chat is the following question. So given this, which direction do you think the ball would go? You can give your answers in the chat. One says it goes down, right, down, etc. Right? So you would do that with whatever information you have in front of you. Down, I guess people are thinking, okay, there's gravity, there's no floor, it would go down. Right? So there's no uh, 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 correct or wrong answer to this, right? So up and down, maybe it's going to bounce. That is the information that you have with you right now, right? So with that, you're going to process, give something. Now, if I show you something else and ask the same question, for example, okay, now we have seen what is going on. Now, if you want to answer the same question, now where is the ball going? Now you see that with a simple experiment, there were many different answers. Now we see that at least a few of you are converging to the same answer, right? So you see that the network is now converging, right? So now given no predict. Now, in order to do that, maybe I'll ask one of you, say, I see, Pankaj, can you tell why did you say right? Although it's obvious, but uh, uh, let us know the chain of thought that you had, and what are the things that you used to say it is right. Pankaj or Tripti, one of you.
I think the past occurrences that is there in the sequence that guides us to that what will be the next action. That's how I see it, because everything is going towards right. And
Yeah. So, in other words, like what any one of us would basically do is to see if there is any pattern in the data, right? So pattern in the data, what you're looking at is different time instances where I showed different frames. And then you see, okay, there is a pattern. Maybe the pattern could be that it's going to go right, but you might be very well be wrong. That, okay, this is the best guess that we can do based on what we have seen. The next instance might go somewhere else, right? So that could also be possible. But in essence, what we are trying to see is I'm trying to look at if there is any pattern. We are trying to learn that pattern and do a prediction, right? So that is what we would also want our neural network to do, right? So if you want to see how it predicts, you want to learn from the past. Again, learning from the past, I need to summarize what is going on in the past, right? So these are some of the things that we would want the neural network to do. I'll state that in English, but then we will see how to put that in math and how we program this for a neural network. So similarly, now, if you look at, if I start looking at the sequence of alphabets, so A, B, C, D, E, F, it is very obvious for many of us because the way we are trained, we can basically reproduce the remainder of the sequence completely, right? So even starting from somewhere midway, H, I, J, K, the rest of the sequence would become kind of apparent to us because we know this. We have spent a lot of time maybe to memorize. We could memorize in a brute force way, or maybe some other smarter way. For example, like, okay, there is, if you want to say what are the colors in the rainbow, at least the way I was taught was to remember this acronym called WIBGYR, and then the colors would basically be the first letters of in the word WIBGYR, right? So there is a way to summarize what we would like to learn. So the point is, we can put an effort to learn a sequence either in this brute force way, like, okay, learn each and every alphabet, or if you would like to summarize it as a pattern. So there is some memory going on, okay? What is this memory? How do I build memory into a sequence when designing neural networks? And while this might be obvious, but if I show the sequence, then it might not be very obvious to many of you, but with a little effort, we can even learn the sequence, which is basically the sequence of alphabets in a reverse order. So we have spent a lot of time to learn something, store it as a memory. This is what we also want to ask our neural networks to do. So we want our RNN, recurrent neural network, some aspect. Now, if I ask you the following question, to recollect what you did since you woke up this morning, if I ask you to narrate the sequence of things that you did, you might be able to reproduce it very precisely. Okay. Now, if I ask the same question, what did you do 1 year on this date, this day, 1 year ago? Now, some of the actions that are repetitive that we normally do, you might be able to recollect those, but unless that particular day was a special day, you might not be able to reproduce what are things that you did on that particular day very precisely. Maybe, okay, if it was your birthday, okay, you did something special, or an anniversary, okay. So you did something special, those particular events that you might remember as humans, we do that. But precisely if I go back in time, right? So if I go 2 years ago, might be that memory fades down. But certain events we do remember, right? So for example, okay, yeah, what the way we do is through something called as attention. So we specify that, okay, this particular event was very important. We do put an extra effort to that particular event and we try to recollect, right? So that is attention. And what is going on also is, as we go back in time, our memory fades out, which is also natural, right? So again, like yesterday, what you did, you might remember very precisely. 2 days back, maybe 3 days back, fading down. 1 week already fades down, right? So there is some fading happening, which is in the memory, which is also natural. We have something called as a long and a short-term memory. We remember precisely over shorter time horizons, longer time horizons. If we want to remember, we need to pay particular attention to that. These are natural things, which I'm basically putting it in words, but something natural for any human, any aspect of memory. And we would like to incorporate these aspects while building a neural network. Okay. So what we will do now is, with this particular introduction, we'll pause for a break and then resume back with some more applications And then we will continue the discussion on neural networks. So let's pause for a break now. I'll come back maybe 55 or so. And then if there are any questions, we can take at that point. Yes, Imut.
Yeah, hi, Professor. So I had a question.
Yes.
When we are trying to instantiate any image data generator,
Hmm.
so it would have some arguments like rescale, or there are some others for brightness or something. So how do we attribute values to them? And yeah, so that is
So image data generator, this should be for data augmentation or
yeah, for data augmentation. Yeah,
yeah.
because let's
So
say if I have an image and I want brighter images of that, I also want some darker images of that. I want scaled up images. I want tilted images.
yes, yeah. So again, the uh, prescription is a following, right? So whenever we are doing data augmentation, you would like to have as diverse set of augmented images as possible. For example, like instead of choosing, say, an image with 3 brightness levels, what you would do is you would choose an image with a certain brightness, certain scaling, and certain tilt, etc. Right? So once you have those, the value to a large extent, what brightness you choose will not really matter. And one way to basically check if it really matters is to again train with different set of hyperparameters. I mean, different set of parameters. For example, like, okay, do I need to scale it like 10 times or 0.1 times? So that those are things that you would check to see if your accuracy is dropping further or increasing, right? So that is what one would do. And in essence, there is no, again, general prescription that it would always increase. It's not very obvious. It could be that, for example, certain augmentations might also deteriorate your accuracy. Because for example, like, okay, you're looking at, say, image classification, and for image classification to detect whether there was an object or not. Now, to detect whether an object or not, by looking at the general class of images, what it would also try to do, for example, is to look at the contrast between the foreground and the background. Now, a certain augmentation might basically remove that contrast, right? So, because of whatever we are doing, so in that cases, the accuracy might also drop. So, what I want to say is that depending on the task at hand, augmentation might help or not help. Uh, Within a particular type of augmentation, generally, um, it might not affect so much. For example, like the contrast level, if you change, then okay, that might lead to a different image. But exactly choosing, there's no formula to figure that out. And if it works, any number should usually work. And way to validate is again like to retrain with a different set of images. Does that
Okay.
answer the question? Yeah.
Yeah. So another thing is that if I have 1,000 images in my training data set, so should a ideal way be to create another 1,000 images with let's say rescaled image, another 1,000 image with let's say the contrast being little bit off, and then use all 3,000 images training?
So, yeah, okay, that's a good question. So, uh, generally, what you would do to begin with is a following. Suppose you have 1,000 images from 2 classes, okay, and class 1 you have, say, 700 images. Class 2 you have 300 images. In that setting, you would focus on augmenting data to generate more data for the image which is fewer in number. So the 300 images, you try to balance it. What is also required is you need to have class balance. to make sure that there is enough representation from each of the class. So in that case, you would now try to augment such that this 300 becomes at least like 650, 700, right? So that is one thing that we have to keep in mind. Now, data augmentation is done to avoid class imbalance. The second thing is now, if at all there is already a good balance in the data, what you would now do is to see if I'm augmenting more data, will my accuracy from 90% become 92%? Okay, so now in that particular case, you can try out one augmentation at a time. Instead of doing all possible augmentations and then start debugging what went wrong. So you would basically do one at a time to incrementally. So if I do rescaling, now 90 becomes 91. I'm not deteriorating. Now do, say, cropping. You take one step at a time. So that is what I would generally do.
Okay.
Yeah. So if you see, like, I mean, there is a systematic way of doing all this.
Okay. And the thing was, Naveen was trying to do this, but when he tried this, the means accuracy dropped drastically, something like from 90% to 40%. So we were also not sure, like, what went wrong. Or...
Yeah, I mean, it could be because of the reasons that I mentioned, right? So, for example, like this MNIST data set augmentation, you would do more damage than help.
Okay.
Yeah. So I would do one at a time to see what exactly, which augmentation that you're using is causing. And also, I mean, before simply throwing it to the model, you can also see what is the, as a human, if you can detect what is going on between 1 and 2 for a reasonable number of classes that you can see through, then the network will also very likely able to do. If you cannot distinguish, then very likely the network will also not distinguish.
Yeah, yeah.
Yeah. Okay. Okay. So let's pause now and resume back. Okay. So let's resume now. Okay. So what we would like to achieve with this network that we build is it should have some memory that we can account for, and preferably we would like to attend a certain portion of the data we are seeing, streaming data we collect. And then what is also natural to expect is that as we deal with more data samples, when I say more data samples, it is more time instances. It is natural to forget something from the past, right? So that is what we would expect and want from our network that we build. So before we proceed, let me show some more examples where this is useful. Particularly, this one is the last one is interesting. So, for example, like you can use this to do prediction, like of text sequences, like what I already mentioned while building chatbots. These are the initial applications where RNNs were conceived, right? So, for example, if you look at this a chatbot from a banking app, you see that, okay, how to open a. If you type this, then the remaining sequence of words show up. For example, a fixed deposit or how to open an account, etc. So these are like the possible options that it would list. What is also kind of familiar to all of you is the email console, for example, Gmail or mail consoles that you see, you type something, it's going to automatically predict the next few words. While doing so, it is important to predict what comes next, but also to keep the context information in mind and to be grammatically all right? So these are some of the things that most of the MLP models take care of. But before doing all that, you require an embedding for a prediction. What is also very interesting is like what's not very apparent, like, okay, English language, maybe we are very used to, but very nicely you can generate sequences of numbers or music tones. So what I'll do is this is one such music sequence generated by the RNN architecture and LSTM architecture, to be more specific. But I'll play this. So I hope you all can listen and will be able to appreciate this. Let me see how to. Yeah. Can you all hear that?
Yes.
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 Okay. So all of you saw that. It's very remarkable, right? So unless like, okay, you are paying attention to some minute details, it is almost impossible to say that this was artificially generated. So basically, you could show a sequence of notes from, say, Beethoven or any of your favorite musicians and composers, and similar to how you would predict what happens in a time series, you could now start predicting musical notes as if, okay, what happens if we extend the sequence? Maybe you're not going to replicate exactly the same ones, but now you're going to train a network so that it generates music in similar patterns, so which is very remarkable. Um, so the bottom line is the time series need not always be like the number sequence of numbers that we have been used to, but it could be audio, images, video, sequence of images as video, time series of numbers, sensor data, etc. So all these can be modeled, and the underlying dynamic pattern can be learned using recurrent neural networks. Okay, so before we do that, let's quickly recollect what is a feed-forward neural network architecture, a perceptron-based model, and what changes from a perceptron to a recurrent neuron, right? So perceptron, what we have been doing so far is, if I have an input, say data, xt, that input data is transformed to a certain label, and the transformation is basically given as some nonlinear functions of the input data. Okay, in particular, our nonlinear function was some activation function times wxt plus some bias, right? So for a single layer perceptron, but you could do this, do something similar with a multi-layer perceptron. And what is important is that you would not pass the information from the output to the hidden layers or the input neuron, but this is the information flow direction, and it is called as a feed forward network. Now, depending upon how many neurons we have, etc., we can get a neural network architecture, and then you basically learn all those parameters as we progress. So you set up a loss function between your label and the output to learn the parameters. You would optimize, minimize the loss with respect to theta, theta being the parameters of the network, right? So W's and B's. Okay, this is what we have done so far. Now, when we are dealing with time series data, you have sequence. I need to extract something from the sequence. Now, to do that, a recurrent neuron, what it does is the following. This is a recurrent neuron, not a perceptron anymore, but what is important is this feedback. It's not just a feed-forward network now, but it is a feedback network. What is fed back is the hidden state. So you have an input xt, okay, as before, the output will be the label yt, okay, at the estimate of our label. Now, what is basically fed back is part of the output. Output is fed as a input. What is important distinction between what we have seen so far is that in a perceptron, you only have one input, okay? Every perceptron has one input. Whereas a recurrent neuron has two inputs. One is basically the linear combinations of the features that go as input. One input, when I say it could be a vector, but one vector. Now you have two inputs that determine what the output is. And this is basically the feedback. Okay. So the basic deviation from a perceptron to a recurrent neuron is that while determining the output y of t, it is still some function of some unknown parameters that we want to learn. You feed xt, the current input, along with something else, okay, that basically determines what the output is. And this something else is what we will see next, right, as we progress. But this is basically something from the past. So we try to summarize something from the past to determine the current output. Okay, so that is what we will see. So in a nutshell, what is deviating from a perceptron model to a recurrent neuron is perceptron has no feedback, one vector input. Recurrent neuron is also an artificial neuron, right? So it is a different model of an artificial neuron. Perceptron was also an artificial neuron, a different model of an artificial neuron. So has feedback and two vector inputs to every perceptron. Okay, now I can think of having many perceptrons, many layers of perceptrons. We will see all that as we progress. Okay, so now let's try to understand with a simple example what is going on. So what we see is a sequence of words, but let's see what is going on here. So now I have an input. This input, this is RNN. Okay, it's the same RNN. RNN is not changing. Input at time t1, t2, and so on. Okay, so the input is part will become more mathematically precise as we progress, but for now, let's keep that abstraction that, okay, there is something fed back, all right? Okay, we will go into the details of what it is as we progress. So at different inputs are being, inputs at different times are being fed to the recurrent neuron. The recurrent neuron remains the same. And what is changing is the outputs. Output T1, you get output O1. T2, you get output O2, and so on, right? So as time progresses, things are changing. Now, what we are seeing on the right-hand side is an unfolded version of what we saw in the left. Okay, so now let's go one time instance at a time. So T1, T2, T3, T4. So these are different time instances, T5 and so on. Okay, time is evolving. At time instance 1, the input is what? What will be again transformed to some vector representation, and that goes as an input. Okay, now you feed that to say this RNN. Okay, it does some magic and it gives you some output at time T1, O1. Now, this is our start time, so there is nothing going on, so it will be a 0 input. Okay, now at time T2, my input data is time. Okay, so of course, what is apparent from this illustration is you would like to predict at output 4 what will be the next input. So what time is it now? So this is what we would like to have as output at time 4. Okay, so now at time 1, I feed the current input what is from the feedback, the second input that it should receive. There's nothing, it's a 0. Next, what you get is basically at time T2, the input is time, but what is fed to the recurrent neuron is the current input and something from the past. This is okay. So something from the past, again, this will become very clear. So now focus on the color code. Okay, so what time is it, right? So every word has a different color. And what this basically means is the following, the illustration. So I'm looking at this evolution of sequence. What has a color? At input time, what goes as an input to the recurrent neuron is the current input as well as something from the past, something that summarizes what was past. Hence, you see that two colors are being represented in the recurrent neuron, right? So it is taking those two as an input. And it will give at output time T2, it will give some output. It's the same recurrent neuron. The recurrent neuron is not changing. Only what is changing is the inputs are changing, the output will change. Okay. When I say it's a recurrent neuron, we are sharing weights across time. So it will become clear as we progress. So that is what you need to understand. When I say it's the same recurrent neuron. Now, at time T3, what is going on is you get the current input, which is and something from the past. And in this particular case, something from the past, immediate past is time, but time had an influence from what? Okay, so time was depending on what? Hence, whatever we feed to is T3 will have an influence from time as well as from what. But as you see, the amount of influence that what plays at time T3 is now reducing. So this is graphical illustration of what is fading, right? So fading in terms of memory that I mentioned. So now you have influence from the current time, past, as well as past. We'll see mathematically all these things, but let's get the intuition in place to begin with. Now, similarly, T4, it is the input, which has some influence, and then there's all the influence from the past, right? So you get the current input, something from the past. Since something from the past depends on its past, and that past depends on its previous past, so the past has information throughout. But the influence of what at time T4 is becoming smaller and smaller, right? So as we go back 1 year, 2 year behind, so memory fades, right? That is the illustration of what is going on. Now, our goal usually is we would like to mimic at for example, when we are doing prediction at time t4, at the output, we would like to mimic the next input, right? So now, for example, what time is it now? If that is a prediction, then I basically have a one step ahead prediction. Okay. Now, all these questions that naturally should occur to anyone, and also that you're asking, how do we decide what should be fed from the past? What is the portion of how do we summarize the past? What portion of output is fed from the past, and so on? This will become mathematically clear as we progress. So what is important for now is the following. We have now a slight deviation of the perceptron, which instead of taking one input at a time, it is now taking two inputs. The current input at current time, as well as something from the past. Now, while doing so, what is static is that recurrent neuron, which means that imagine that every neuron has associated set of weights and biases. All these remain the same for each time. That is what we also ideally wanted. I did not want to have weight and biases per time instance. I will fix that. So that means the neuron is the same. What is changing is, imagine that there is this neuron, and the same neuron, the inputs are changing, hence the output would change. So it's the same box, I am feeding different inputs, right? So at time t1, I feed these two inputs. Time t2, the inputs are changing, but the box remains the same. What goes on, how the box produces the output remains the same. Since the input is different, the output will be different, right? So this will become mathematically clear as we progress. Okay. So now by doing so, what we are trying to basically leverage is to see if we can capture any dynamic pattern that is evolving over time. Okay. So this is a simple graphical illustration of what is going on. Recurrent neurons different from perceptrons in that now it can influence the output based on the past output. Recurrent neuron, because it has this additional input, it can have influence from the previous time instance. If I look at perceptron, then perceptron did not basically have any of this, right? So which means that the time instances were independent and I could not model sequences. Okay. So now with that basic notion in place, let's see if we can answer this poll question. To set up the next discussion. Let's take um, a few more seconds. So why are they useful for handling time series data? And what do we need to enable it to handle time series data? So I'm going to end this poll now. And as majority of you have rightly identified, recurrent networks, recurrent neurons in particular, are capable of modeling or capturing temporal dependencies because there is a connection from the previous time instance to the next time instance. Now, if we leverage that connection effectively, it can capture temporal dependencies. Now, since beginning I've been mentioning that. Now I don't want to, so if I'm dealing with say 100 time steps, I don't want to have like 100 W's and B's. If I do that, then basically the number of parameters will grow with number of time instances, which is not efficient, right? So I can have a text with 100 words, I can have a text with a sentence with 1,000 words, so on, right? So that that varies from application to application, but the network that I design should be agnostic to that particular size of the input. Very similar to what we had for CNNs, but now the input is varying across time. It is not a fixed length vector. So what we desire is that RNNs do share weights across time. Now, just to understand again in a slightly different way of what MLPs did by viewing, say, the layer index as I should not be confused with time, it is the layer index. Okay, so input is layer 1, hidden layer is layer 2, and so on, right? Output is layer n. So now, if you look at this, the transformation is going on as follows. So I have data at layer I minus 1 that is linearly transformed with some nonlinearity to get the next output. So there is no additional input per se here, right? So there's only one. Okay, so now I get two features. This is example 1, and then I get x1, x2 related to example 2, and so on, right? So that is how we form our mini batch and do the training. And for every example, I get an output, okay? But in all these cases, the input data was a fixed length, and we assume that the training samples are independent, which means that example 1 could be digit 1, example 2 could be digit 9, or so on, right? So what we would like to now do is handle sequences which are of varying length, which means that I need to have a sequence, say x1, x2 till x100, which is evolving over time, which is not a fixed length, and also capture dependencies across time. Okay. So now, in order to do that, so these are the two main desired goals that we have. So one is varying length, and it should capture dependencies. Okay. So now to do that, what we introduce is the so-called recurrent neuron, which I introduced pictorially. Now I will define that more formally. So what we would like to do is we would like to model sequences. Sequences, when we say modeling of sequences, what we are basically interested in is to model a sequence of data, in particular, predict a certain output at time yt by taking into account all the past inputs. So all the way up to x0. Having seen all this data, what is the likelihood of the output yt, where yt would be, say, our estimate or guess of what happens at xt. So given all this past historical data, past data, what is our best guess for what comes next? So this is mathematically how we would model any sequence. It is of varying length. Now at time t plus 1, I would like to predict yt plus 1 given xt all the way up to x0. Okay. So now if you look at what is going on in a recurrent neuron versus perceptron is the following. Recurrent neuron, let's focus on this particular picture and then we will proceed further. Recurrent neuron has two inputs. One is x, the input from the current time, and you take some feedback from the previous time. The way you should interpret any such recurrent neuron model is by unrolling it. Okay, so at each time, we have an input, which is the feature that we feed, and there is something from the past that is being fed. Now, as before, every arrow has a set of weights associated with it. Let's call it as Wx. Something from the past, this also has weights associated with it. That is Wy. Okay, so now you combine the features using Wx at time t1 or t minus 3, combine something from the past with another set of weight matrices and biases. That linear combination is fed to this perceptron. Okay, so perceptron or recurrent neuron can be viewed as perceptrons with additional inputs, where every time I basically have two inputs. Every arrow that we see here has a weight associated with it. Okay, arrows are the same. Now, what that means is, if you see here, input is varying because it is saying different time instances, xt minus 2, xt minus 3, and so on. The arrows have associated weights, but the arrows do not depend on time, or wx, wy does not depend on time. There is no wxt. Okay, no, we only have wx, which means that for all time instances, we are using the same w. Okay, now what is the consequence of this? So if you look at, let's take a look at this particular example. So that the output at time 1 depends through some parametric function, depends on the current input and the past output. Okay, is that clear? So we have, let's take a look at this particular segment. We'll worry about what this function is. Now, the output at time, any time instance, depends on the current input and something from the past. Okay, so this is current input, past output. Now, which part of the output, etc., we will worry about that as we progress. So the index or the subscript is time. Okay, so now the output at time t2 is again some function of the current input, which is x2, and the past output, right? So what happens next? If you look at the next time instance, it depends on the current time instance xt minus 1 and yt minus 2, something from the past. But what was our y1 depending on? It was depending on some other, through some other function, let's call it as say f2. It depends on x2, x1, and y0 is 0. So I'll just terminate at this point. So although from what we see, apparently through this diagram, the current output depends on the current input and the past output. But the past output was depending on the input at that time and its previous one. So in other words, the output at time 2 depends on input at time x2 as well as x1. What is f2? So this is nothing but f of x2 and f of x1 y0. So this is basically equal to 0. So that's why I'm not writing y0, right? So this one I'm writing it as f2. Similarly, y3 depends on x3, x2, and x1 all the way up to x0. So in general, yn depends on xn, xn minus 1, all the way up to x0, okay, or x1, right? Depend, I think we are taking x1. So it depends on the current input all the way up to the previous inputs going all through x0. Is that clear? So any questions related to this particular logic?
Professor,
Now, how do we take these functions? We will see as we progress. Yes, go ahead.
why should it be called as fn? Because the function remains same, right?
Yeah, so the function here at this point remains the same. Okay, but what is, I want to simply write it as a function of x2 and x1. So this entire thing, I'm calling this as some other function f2.
Okay.
Okay, so but at the input, it is, yeah, x1. So x1, y0, it is going through the same function. But then to just simply compactly write it as a function of the inputs, I'm introducing a new function. But if you look at what is going on, the dependency is clear, right?
Doesn't the nature of function change with the dimensionality? Because the dimensionality
Yes.
is changing, right?
Yes. So what, I mean, we will specify for now, just imagine that f is a box that depends on a few things. So it takes some input and gives you some output. We are seeing what that output, how can that output be characterized, what all it depends on. How it depends on, we will see next. Okay.
And have we tried this, like combining the linear combinations of these inputs over time, as well as then applying nonlinear functions and then combining the output
We will
as
see.
input?
Yeah.
Yeah.
In the next slide, I will make it a bit more specific. Okay. So we will see, we'll basically specify what this f is in a second. But for now, going from this illustration to something bit more specific, is that what we saw was that at time t2, it depends on the current input as well as something from the past. So something from the past is O1, which kind of summarizes what was going on at time t1. Okay, so now that is being fed to the input, right? So now how do we take that? What is the portion, etc.? It will become clear. And it depends on the size of the inputs and so on, but we will see all that in a second. So any more questions related to this particular logic and contrast between perceptron? So in perceptron, as you can see here, there was nothing going on with the past, right? So this was basically, if I put time t to all of this, so what you're basically getting is f of xt. There's no second argument that we queue, right? So this was basically our output. In contrast, here you have at any point in time, if you look at what a perceptron is, it is taking two inputs, right? Two arguments. That is the basic contrast.
And why you say no wxt, you would need some weights to
Yeah, we
combine
will
the
see.
x.
Yeah, yes, we will see that. But the function, if you look at from a function, one argument versus two arguments, and if we unroll that, like what we are doing in the second picture here, we see that although at any given instance, explicit dependencies from the current input and it depends on inputs all the way up to 0. Biases, etc. We'll see what it is. What happens in the past. Okay. So now, what is the math going on? So we have xt, the input at current time, and I also have output from the previous time. Okay. Now, I need to generate the output at current time. Okay, so in order to do that, what we do is the following. I take a linear combination of the features at current time with a weight matrix Wx. So this basically incorporates how much the current output should depend on the current input. How should I combine my features? Through another weight matrix, Wy, we decide how much information from the past should have an influence on the current output. So you take a linear combination of the past output, and there is a bias. And all this, as usual, will be through some activation function like ReLU, tan hyperbolic, or so on, right? So that is an activation function. Now, again, we have dependency from the past tells influence from the past, how features at current time should influence the output, the bias. Okay, so that is one thing. Second thing, you see that the parameters of the network now are, so now we are only looking at a single recurrent neuron, right? So whatever we discussed before, having multiple of these uh, uh, recurrent neurons as a deep layer, etc., all that is possible. But now what we are looking at is a single recurrent neuron of multiple layers, multiple outputs. So Wx, Wy, and B. These are the parameters that we would like to learn. And not Wxt, Wyt, and Bt. We don't have this, right? So there's no dependence on time. So for t is equal to 1 all the way up to say 100 or whatever capital T, I'm using the same Wx, Wy, and B. I'm not using Wx1, Wy1, Wyt, Wxt. Okay, I'm not using that. So that is very important. Okay, so they are not time dependent. Is that clear?
But would they vary across training epochs?
No. So they would vary because of the training procedure. So you initialize Wx, Wy, B, that is initialized. Okay. Now, once you initialize, you go through mini batch 1, mini batch 2, mini batch 3, that would settle down to something as the training converges. Is that clear? So
Yeah.
very similar to what we were doing previously, right? So you start with an initial Wx. So the only new change now is this particular set of additional weights. Okay. So before we did not have this, right? So before, if you want to simplify a recurrent neuron to a perceptron, simply Wy should be 0. There's no influence from the past. Now we have additional influence from the past. The way Wx, Wy are trained are through an iterative process using gradient descent. So across epochs, you start with some random initialization and then you train for multiple times. Okay.
Thank you.
Is that clear? Any questions? This is very important. So once this is clear, then the rest of the story is basically obvious, right? So nothing much except for, again, putting this in a particular way and seeing what are the applications. So this is the main concept behind recurrent neuron and any sequence model, right? So if you look at transformers also, the way you would have the influence from the past, that particular way could be different. But what is the basic idea of recurrence? That remains the same, right? So you might have certain nitty-gritties that would change, but you have some current influence from the current input and the past output, right? So that is fundamental to any sequence model. Now, let's take a look at how the parameters size, etc. Vary. So suppose at every time t, right? So now this is another way of visualizing what is going on. But say at every time t, xt, we have, for one example, each example, we have p features, right? So this is number of features. Okay. So now we have p features and yt, suppose this is the length of this vector, right? So previously I was only showing in this picture one output, right? So we had a perceptron with a single output. Later on, we put them together to get perceptron with multiple outputs, right? Multiple outputs. This is a scalar, but we can have a vector as well, right? So the output is a vector. So let this be of size n times 1. This is the number of outputs at each time. Okay, so for each t, right? For every t. Now, once you have this, basically the size of wx and wy are kind of determined, right? So now I want this to be of, say, a vector in Rn, so n-dimensional vector. So suppose this is of 5 times 1, then n is 5. Okay. So in this particular example, I have 5. So in this particular example, n will be 5. 1, 2, 3, 4, 5. Okay. So now for this particular size of x and y, wx will be of size n times p, because it takes p inputs, gives you n outputs. Wy will always be a square matrix of size n times n, because the previous output was also n. It takes n, gives output n. And then b is of size n times 1. Okay, so that is basically giving you the output. So in this particular setup, so suppose, say we have 3 features, x1, x2, x3, output is 5. So then you can basically use the numbers. So the number of parameters are adding all this. So the total number of parameters for this particular illustration is basically n times p plus n times n plus n. Okay, so this is basically n times p plus n plus 1. Okay, so this is always the number of parameters. So it is basically the number of outputs times number of features plus number of outputs plus 1. Here you see the number of parameters again does not depend on T or capital T, right? So this is the main essence. Okay, now what is WT, right? So WY is telling how much influence should the current output have from the previous outputs or previous inputs, in other words, that is determined by the task at hand. Eventually, what you will do is you will again set up a loss function. You would train WX, WY, etc. And depending on the label that you would like to predict. For example, if we go back to this illustration of this movie was bad and blah, 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 and sentiment analysis. So maybe what is relevant for the output is to get the keywords of bad and so on, right? Long, bad, boring, etc. So these are the keywords. So WY is going to determine that how much weightage should that have, right? So that is what it is going to determine automatically based on the task. You want to figure out what this WYs and WX and Bs are. So there is a bias, there is weights, WX, WY that we need to learn. Okay. So any questions related to this particular architecture? Okay. I hope this is all clear. Now, what is maybe worth to re-emphasize? Do that through a new slide. The training process, right? So the training process, again, you will have a data matrix X. This data matrix has the following, right? So you would have example 1 time 1, example 1 time 2, all the way up to example 1 time t. Okay. And then if you're doing sentiment analysis, you would have a label associated to that. You can have one label for every time instance if it is like time series prediction task, or you would simply have a 0, 1 in case of sentiment analysis. Now, example 2, you would have the same. Right? So this is example 1, example 2, all the way up to example n. Example n. Okay, is that clear? Time t, example n. So you would have y label 2 and yn. So this would be your input data. Now what you would do, you would again for training, you would form mini batches. So for example, if I form mini batch of size 2, then you would basically have these 2 in your training data. So you would form mini batches across time, right? So that is what changes now. So this is say time 1, time 2, and all the way up to time t. Okay, so you have examples, you have time. In contrast to the data for perceptron or MLPs, we did not have time 2, time t, and so on. What we were basically doing was we had many examples. We are forming mini batches of these examples, contrasting with a label. Now, what we also would like to exploit is the dependency, right? So dependency across time.
Professor, sorry to interrupt. From the previous slide, there was one P, as in number of inputs are P. So,
yeah. So P in this particular cases, each example, say example E at time t, this would be of size P times 1. So
okay.
yeah, so imagine that this was, see, this is the input for the MLP. We had P features.
Yeah.
What we have is, we have P features for each time.
Okay.
That is P. Okay, so each entry of this matrix is a vector that is of length P.
So this x1 to xt, which is there, is that capital T same as P?
No. So
each x1 has a dimension of P.
is equal to 1 to T, right? So I have different time instances. So for example, like, yeah, so example 1, what time is it, right? So for example, in this particular case, we have T is equal to 4 time instances, T1, T2, T3, and T4. I'm converting each word to a P length vector.
Okay.
Okay, so time is converted to a p length vector and so on. Okay, so that's the embedding.
Okay, so each of x1, x2, all of these are p-length vectors.
Correct.
Okay.
Yeah. So now if we, let's see if I can go back to maybe this picture, right? So yeah, we converted. So p in this particular case is 4.
Okay.
So what is n then?
So now, okay, so now I would like to train. So what you see is basically one example. Now I have many such sentences in my corpus. Okay, so that would basically let the network train. So for example, MNIST image, I had 70,000 pictures which had many examples of digit 1, digit 2, digit 3. Now imagine if I have to do a sentiment analysis of hit or flop. Now example 1 is this movie was bad and long. Example 2 is, so this is with label 0. Now example 2 is this movie was horrible and boring. That is example 2. So you have like different ways of telling that this is a flop movie, right? So those are different examples. So digit 1, you had many instances of digit 1, but it's not a repetition, right? It's like, okay, it could be with a slight rotation, something else going on. So these are examples. So you will have many sentences from class 0, many sentences from class 1, and put together all the training data that is capital N. Is that clear?
Yeah, it is. Thank you.
Yeah. Okay, so NPT. Okay, so any more questions? I think, I mean, that is important to understand these things. So now, yeah, it could be that, okay, I mean, the label that you get is a 0, 1 label, or it could be label per time, right? So for example, again, if I go back, if I go back here, so in this particular case, we did not have labels for each of this, right? So there was no output that we got. But so you only get one label. But on the other hand, for this, what time is it now? Close and open. So in this particular case, if we want to match every output, so you require labels for each of these outputs. Okay. So output, the messages, the output can be a scalar. I mean, the label can be a scalar per example, or it could be a vector per example, vector of length t. Okay.
How is how is WY n cross n? Can you please explain that again?
Yeah. So y is always, so all these y's, y for any time is of length n. Okay. So if you look at yt minus 1, this is n times 1. Yt is also of n times n. So if you look at what is that, I think there should not be a transpose here. So what takes n length vector gives an n length vector, it should be a square matrix. Okay. So it has n inputs and gives n outputs. So it should be a square transformation. Okay. Okay, so now let's take this poll while we also put these dots together in place. Yeah. So basically it is about summarizing what we discussed so far. So let's end this poll a few seconds. Okay, so as we have discussed so far, the output at any time depends not just on the past input, but all the past inputs up to time 0. Okay, so that is important to keep in mind. Also, as I have emphasized enough, that Wx, Wy does not depend on t, which means that we are sharing parameters across time. So Wx will be the same at t is equal to 1, same at t is equal to 2, and so on. So we are sharing those parameters. Okay. Good.
I still don't, sorry, to litigate this, I still don't understand how is n cross n, so n cross t, is that not Wy?
No. So the way you should see this is as follows. Let's focus only on, say, with Wx is equal to 0. So I'm showing this for one example, right? So this is t some phi of Wy at yt minus 1. Okay. So now b is equal to, this is an example with Wx is equal to 0 and b is equal to 0, just to
Yeah.
illustrate. So now, okay, so it is clear in this case, it is n times n, right? This is n times 1, this is n times 1. Is that clear? So this is with one example, okay? So now, what does it mean? So W1 is phi Wy y0, W2 is phi Wy y1, right? So that is what this equation means for t is equal to 1 to t. So each time I'm still using an n by n matrix. It does not depend on t. Okay. Furthermore, now whenever we do batching, what you would do is, like example 1, t minus 1, all the way up to, say, example, say, your mini batch size, t minus 1, this is all going through the same W. Again, no dependence on batch or time. And here the output would be yt for batch example 1 all the way up to yt for MB. Okay, so this is how you would implement in practice, but as you can see, this is still n by n. Is it clear now?
No, sorry, but I think we can move past. I don't want to hijack everyone's time.
So yeah, I mean, it is like n by n, so n inputs and n outputs, right? So there's no, it is not depending on t. That is what you need to think about. If it depends on t, so which means that for every time instance, I'm using a different W, which I'm not doing. Okay.
Sir, I have a question. So
Hmm.
when you say, for example, what time it is, then predicting now or whatever the next sequence. So you were saying till it reaches the time T5 or T4, right? The T0 input value diminishes. Like what is the T0 value, right? The input value. So how is it like I'm not able to understand because still that has relevance in that particular sentence, right?
Yeah. So it has relevance, but the point that I was trying to make there was, since we are not specifying anything particular, that okay, focus on time instance t0 more than time instance t is equal to 5, right? So all the time I'm treating equally. Now, what is natural to expect is that although there is dependence, right? So you see that yn depends on x1, but because of the linear function that we are using, the dependence of x1 on yn would be much smaller than the dependence of xn minus 1.
Yeah, that's correct. Mathematically, I can understand, but when you
Yeah,
speak,
you don't want that, right? So in
yeah,
practice, yeah, I
yeah,
mean, you would like to emphasize. So yeah, we are building the story.
okay,
We'll see that, okay. I mean, that also, I think, brings to my next point that it has limited memory, right? So we will see that. I mean, so this is natural steps to take, but it has some disadvantages. We will see what that is and how to overcome those as we progress.
okay, sure. But just one question: mathematically, it reduces the value of the input zero at t0. So how, when we move further, let's say there are, for this example, only 5 or 6 sequences, but when we go for complex problems, right, there will be thousands of sequences maybe. So there, how can we get the relevance of the t0? That is where my like
We will see. Yeah, we
okay,
will see.
okay, sure. Thank you, sir.
That is also yeah, I mean, so there is also reasons why recurrent neurons people are not happy, and then they um, in put together this transformer model, right? So we'll see,
Okay, sure.
but not today's lecture, but we will see cover this as we in this module particularly. Okay, so now so whatever we discussed so far was capturing the memory, right? So this memory or recurrent neuron basically has some influence from the past. So it is capturing something from the past and can be seen as a memory cell. And this portion of whatever we are feeding from the previous time instance is called as the memory, or often called as the latent space or a hidden space, right? So these are the terms that are typically used: latent or hidden variable. Okay, so that's the state that we are trying to maintain. Okay, and in practice, what happens, like the sentiment analysis, often we would like to decouple the output and the state, right? So output can be a 0 or a 1 binary variable, but the state need not be a binary one, right? So you can have, say, an n-length vector, and that n-length vector is further transformed into a Boolean, right? So that could be a scalar Boolean, for instance. So that is what is the more general form. What remains as before is that we have some hidden state that we maintain throughout, except that we have another variable to denote the output. Okay, that is a slight change in what we have compared to what we had before. So we maintain two variables distinguishing the hidden state from the output. Output could be, as for example, a 0, 1, or it could be something for a particular task at hand, but the hidden state can be different, right? So that is the distinction. And this is a more general form of a recurrent neuron architecture. And although there is no uh, stronger theory associated with this, but what is like what I was mentioning, what is evident from the experiments is that the recurrent neurons are only capable of capturing short-term patterns. They cannot model long-term dependencies, and typically it is about 10 steps, but varies from one task to other task. So the memory fades down as you go further and further. The context information is lost, although this is designed, but what is experimentally observed is that this particular recurrent neuron architecture has limited memory. Okay, so now the more general form, as I mentioned, is decoupling the output from the hidden state. So let me again re-summarize this for the general case. So suppose my xt is, say, p times 1, yt is the output that we desire is q times 1, and the hidden state is n times 1. So this is the hidden state. This is the output desired, and this is the input size, right? Feature size. Okay, so now for what we do is HT is WX XT plus WH HT minus 1, right? So I'm maintaining difference between X and Y and H so that it can have different meanings. Okay, so this is the state, how the state is evolving. So it doesn't depend on time, very important. Now, output can be different from the hidden state. So this is some transformation of my hidden state plus some bias. Okay. In the beginning, what I introduced was for a special case where y of t is equal to h of t. Okay. So that could be a special case, but more generally, I would like to maintain a distinction between the hidden state and the output. So Wx is of size n times p. Wh is of size n times n. It's always a square matrix. Wy is of size q times n. Okay, that's the input output mapping. Similarly, the bias bh would be of size n times 1 and by would be of size q times 1. The total number of parameters that you would like to learn in this particular case is the following. Okay, in all these cases, you see that the parameters do not depend on time, depend on time index. So I don't have to have as many Wx matrices as the number of time steps. Okay, so now having introduced this, now we will see how is training typically done. Okay, so now suppose our problem is to do one-step prediction. So one-step prediction, what that means is at every time, say y2 is the output here, should be a guess of what comes at time 3. And y1 hat should be an approximation of x2 and so on. Okay, and y0 should be a guess of x1, right? So I'm trying to do one-step prediction where every output that I get should be a guess of what would come next, right? So I say, for example, that sequence, what time is it now? When I feed what, the output should be time. When I feed is, it should be it, and so on, right? So it should be one step ahead prediction. That is what we are trying to understand. Now, the loss function for this particular case, the way we would set up this loss function is, I would like to minimize the discrepancy between the guess that we make, the output, and xt plus 1, right? So this is the loss function. And we would like to do this for each time step. And this is our loss function. And as you can imagine, this loss function would depend on Wx, Wh, Bh, Wy, By, right? So it depends on all these parameters. Now you take a gradient with respect to all these unknown parameters, and what you would learn doing a gradient update is the unknown parameters, right? So the process is the same, except that the loss function, the way you set up the loss function is different, right? So this is for one-step prediction. Okay, is that clear? So any questions related to this? Okay. Okay, so now what is important to realize is that we are setting up a discrepancy measure that is for a particular task. And when we are measuring the loss, say at time capital T, there is an influence of the inputs all the way up to 0. But also what is going on is that since it is the same W's, there'll be dependence of all the loss functions. So loss function at time 0 will also have W, all the W's and B's. Loss function at time 1 will also have all the W's and B's. So there is a lot of dependencies. Hence, what you're doing is you're not just backpropagating across that particular computational graph, but the computational graph that we saw in the last 2 lectures that will also grow with time. Okay, so that is something that would make RNNs nasty as well, but we will we don't have to worry about that, but the automatic differentiation is going to take care of that, but we have to be aware of what is going on there. So now we have set up this basic architecture. Now what we will do next is to see a few use cases of RNNs as we progress, and maybe if time permits, one simple RNN block we will see, and then we will continue the discussion on this. For example, understand GRUs, LSTMs, etc. in the next class. Now, we have understood recurrent neuron takes input from the current time as well as something from the past. Now, this particular sequence modeling technique can be used in the following 4 architectures. I'll tell what the applications are as we progress, but at a very high level, you can have these 4 models. The first one is called as a sequence to sequence model. In sequence to sequence model, as the name indicates, the input is a sequence X, 1, 2, 3, and so on. The output is also a sequence. Okay, so you get a sequence of input, sequence of vectors as an input. The output is a sequence of vectors. Now, the second architecture is a subtle variation of the first sequence to sequence architecture, where the input is a sequence of vectors, but the output is just one vector. I don't worry about the vectors at previous time. I only worry about the vector at the last time instance. So we have seen already a use case of sequence to vector. The other architecture commonly used is the flip of this, which is the input is a vector, but the output is a sequence. Okay, so I would like to generate a sequence having seen one vector. A very powerful architecture is the encoder and decoder architecture, where you get a sequence of vectors as an input. Now, what you care about is the latent representation at the last time instance. You don't worry about the individual outputs, but then this is kind of encoding everything that was going on with the input sequence. Now, that decoder, there's another architecture, which is again taking only the latent variable from last time instance as an input, and then starts producing a sequence. Okay, so 4 architectures: sequence to sequence, sequence to vector, vector to sequence, encoder decoder architecture. Encoder decoder architecture is popular in different contexts. For example, autoencoders that we'll see later on also uses this encoder decoder architecture, but we will see now with some examples of these 4 architectures. So sequence to sequence, the main application of that is the sequence generation, like this email console application. So every time you type a letter, you are interested in predicting what comes next. So given a sequence, what is the likeliness of getting a next sequence? So E, you want L, L, you want L, and so on, right? So hello. Or if you're looking at a particular application, so for example, cash flow is high, you would like to predict what comes next. So I would like to predict a sequence like in the email console. Sequence to vector, we have already seen this. You give a sequence of vectors and you're interested in a vector. You're not interested in predicting what is going on here, but you're interested in only one output. This particular output can be a function of the outputs like what we get here, right? So this is the case where your H and Y should be different. So here you have some hidden state that is going on, but then the output is kind of, say, a two-length vector. You can have a larger length hidden state. Hidden state could be of length, say, n, and the output q size, the size of the output that is q could be 2, right? Like in this example. Is that, I hope that is clear. Now, vector to sequence is another interesting application. For example, in image captioning, right? So you see this image, which is extracted using the features are extracted using CNN, for instance, and the output is that last layer of the CNN, the flattened one. And now we feed that as an input. Now you start generating a sequence. For example, in this particular case, you have like a man wearing a hat. Okay. So now what you would like to generate is identify the objects, produce it as a sequence, like a straw hat, or it could be like some other hat, right? So that is when vector to sequence is used. So you can, again, like, okay, summarizing video, summarizing, say, a text embedding and so on, right? So that could be an application for vector to sequence. The popular application, which is of interest to many of these big industries, is machine translation, right? It has been a, a topic of research since many decades, like to translate from one language to the other for obvious reasons. So in machine translation, what we use is the encoder decoder model. For example, imagine this Google Translate console. So what you would do is you would, if you visualize what goes on, so you would key in something in, say, English, and then you would like to change the language to which you translate. For example, it could be Hindi, Tamil, Telugu. You would like to change the translation. What is the input? The input is the same sentence. And Translate provides you that option to change from one language to the other to which it has to be translated. Now, whenever you want to do this translation, what you would do is you would encode that sentence, keep that summary. That goes as an input to a decoder. The decoder could be a Telugu decoder or a Tamil decoder and so on. So you click what is that, and it would start generating. So in this particular case, I think, I think it is German to some English to German translation is going on. So what is going on is like you don't feed all the outputs, you only feed the latent space state as an input, which is the encoding of that sentence. So you summarize that sentence, that is given as an encoder. Okay. So these are typical for architectures, and whatever tasks you come across with time series data, language tasks can be fit into one of these 4 architectures. Okay, so again, like at the output, what should be obvious at this point for all of you is that, say, for example, if I'm doing sentiment analysis, so now you are using a binary cross entropy loss at here, right? So to get 0, 1. Now, if it is like a multi-class sentiment analysis, like one of, so it could be like you would like to rate a movie, and one like rating could be like good, very good, bad, very bad. Only one of them could be active at any instance of time. That's again a sequence to vector. But then at that case, you would not use a binary cross entropy, but you would use a softmax, right? So that is again like whatever we had seen before, you put that in a different context. Okay. So a bit more detail about this encoder decoder architecture. So again, like we will come to this again when we're discussing this NLP module, where the translation is like for I drink milk. Okay, so now what you do is you would hash it to a different vector using some embedding uh, uh, procedure. So what goes as a vector as an input, and then you're only passing the latent state to the decoder. Okay, so the latent state, the decoder could be again like say a vector to vector, like sequence to sequence, or a vector to sequence model, right? So in the previous illustration, this was the decoder. Decoder here was a say a vector to sequence, but it can be a sequence to sequence. So that is why I'm again elaborating in a different picture here. So in this particular case, you could give as input the encoded state where you output a sequence. Now this can be fed back as the next input, right? So that can be again made a sequence, a vector to sequence or a sequence to sequence model. Okay. So now let's take a poll to see where we stand. So suppose I would like to, it's a different application where I'm doing time series prediction. So what is the architecture that one should use?
There is no option for vector to sequence here in the poll, I guess.
Okay, I see. I mean, yeah, maybe there is some typo while uploading. The last one should be, instead of sequence to vector, it is vector to sequence. Because like some typo while creating this poll, I guess. Okay, I'll end this poll now. Okay, so now when we are doing time series forecasting, what you're basically interested in is, depending on how many variates are there in a the time series. For example, if I'm only interested in predicting the stock price, it is one value, right? So then what I'm inputting is the sequence of uh, prices or index values, and then the output is a sequence of index values. So it is a sequence to sequence. You could use a sequence to vector, for instance, to tell something more than uh, sequence to vector. For example, you would use when you're predicting whether should I buy or sell. Okay, so if that is the decision that you would like to make, so then you feed a sequence of indices, and then buy or sell is the decision that you would make. That is when you would use sequence to vector. You would not use vector to sequence in this particular case, but encoder decoder is also not the one that you would use. So you're feeding in a sequence. It could be a sequence of scalar, sequence of vectors. You're outputting the sequence of vectors at each instance of time. Okay. Good. So now what we will do is, with this background, we will look at one simple example and maybe one snippet of simple RNN. I would require maybe 8 to 10 more minutes before we can wrap up today. To look at one simple example, and then we will build upon this next week to look at these more complicated architectures, which would specify what to remember, what to forget, and so on, like what the discussion already came up. Okay. So now let's take a look at this simple pedagogical example where the goal is now to predict the uh, the time series, which is given here. So what we see is basically, say, three examples: example 1, example 2, and example 3 of time series data. And you have seen the input is now you get time series for 50 time snapshots. So t is equal to 0 to t is equal to 49. That is what is the input, and you have many examples of that. Now, given this, our goal is to predict what happens at t is equal to 50. So t is equal to 0 to 49 is known, right? So you know that x of t. What happens at x50, right? That is the goal. And you have many training examples. So of that form, right? So where 50 snapshots are given, 51 is what you should predict. Now, if you would like to solve this problem, one way is a very stupid way, no learning going on at all. I can simply use x49 for x50. Okay, that's a stupid way, but maybe it works, maybe it doesn't work. Okay, so what that means is I just take the previous value as my estimate for what comes next. A more involved way of doing it is I can use a multi-layer perceptron where I give this 50 length vector that I have, x50 times 1, to this multi-layer perceptron to predict what is x at time 50, right? So I just don't worry about time series. I just treat that as a fixed length vector and I take the output. Now, in this particular case, you see that you require 50 parameters with W and then one parameter because of the bias. So you have 51 parameters. Okay, so this is another way of doing it. Now, the neural network, recurrent neural network way of doing is the following. So what you would do is at every input, you use a sequence to sequence model. So I'm feeding a scalar 1 times 1. X0, I'm predicting what would be my estimate of X1. I would predict what is the guess of X2. I keep on doing it all the way up to I hit X49. This is going to give me an estimate of X50, right? So this is a sequence modeling way. Instead of doing MLP, I can still do forecasting. Now, what you basically see is that how would we do that using a RNN model that we discussed. So what you would do is you would use a scalar Wx because I need one output. Input has one feature, 1 times 1. So Wx is 1 times 1 times xt plus Wy is times yt minus 1 plus b, right? So this is what I would do for yt. I keep on doing this, and y at time 49, I would use that as my guess for 50. Okay, so now if you look at this, you only have 3 parameters. This is 1 times 1, this is 1 times 1, and this is 1. So in total, I have 3 parameters to learn compared to 50 parameters, because 51 parameters in an MLP, because in case of MLP, there was a dependence on time. Now, because if the problem changes, now I'm given t is equal to 0 to 100, predict 101, you would get 102 parameters. So you see the dependence on time, but in case of RNN, we don't have that dependence. Okay, I hope now you're able to appreciate what is the advantage of the sequence to sequence model. Now, how would you code this using Keras? Okay, a simple way to code this in Keras is the following. We would, instead of having a dense layer, I would use something called as a simple RNN. Here, it is a number of neurons, which is basically 1 in our case. So in the previous illustration where so in this particular illustration, I had 5 recurrent neurons. Okay, that is going to give me a vector of length 5 at the output. But now for this particular example that we are looking at, I only require a scalar output. So in this particular case, n is 1. And again, h and y are the same. I'm not maintaining a separate hidden state. So if you want to do that, then you basically do the following. Okay. So this is a way to model a sequence to sequence architecture where the sequence is basically a sequence of scalars that you output. The input is a sequence of scalars. Okay. The main advantage is that you have parameters that are independent of the number of time steps. Okay. Now let's take a look at another example, right? So maybe with two different variations, which is for again understanding say sequences for sequence of words. So what you have here is a sequence of words. I am Groot, right? So some text. Now here I use a simple RNN with 4 recurrent neurons. What that basically means is every output will be of size 4 times 1. Okay. So 4 times 1. So input is of size, say, I have 3 inputs of size 2, right? So that is the length of the embedding. So this is 2 times 1. Now, how would you code this in TensorFlow? So you would basically import Keras in TensorFlow. And then, as I just explained in English, so you would basically give it as a simple RNN, right? So what changed before was instead of using dense or conf 2D, I'm giving simple RNN. Okay, so now with this, you would be able to code a simple RNN model. Okay, for doing time series. So you will play around with this time series example that I gave. One subtle change, the other argument is this return sequence is equal to true. This return sequence is equal to true. If you notice the difference between the first picture and the second picture, this is kind of a sequence to vector model. This is a sequence to sequence. Now, Keras by default, the argument would be for a sequence to vector. In case you would like to have a sequence to sequence model, then you need to give this additional argument called as return sequence is equal to true, which is basically giving output for every time. This is a subtle difference, but if not, then the default is this is only in Keras. Default return sequence default value is false, which means that you don't see the output at each time instance. So this is a hidden state. Okay. If you want that to be true, then you basically have this return sequence is equal to true. Okay, so yeah, so with this, I think this covers basically more or less what I had planned for today. And then we will build up on this to understand LSTM, GRU, and a deep RNN architecture, and maybe with one other example as we progress next week. So to quickly summarize, what did we see today? We have seen a contrast between perceptron and a recurrent neuron. Recurrent neuron, as we are seeing in this picture as well, takes 2 input, one from the current time, one from the past time, as a hidden state or a latent state. These things can be put together in 4 popular architectures: sequence, sequence, sequence vector, vector sequence, or encoder decoder. And depending on the application at hand, you would use one of these 4 architectures. Okay, so coding wise, all that changes now is dense becomes simple RNN. Okay, so that is what changes for a simple recurrent neuron. What we will do now is like, okay, you will have to play around with this implementation for the simple time series prediction. Once we have done that, next week we'll have a bit more understanding of what we are doing. So I will tell some more finer details about these architectures. 2 more useful architectures, that is GRU and LSTM, keeping in mind that so far we are not doing anything specific to ask neural network to remember something for a longer horizon of time. Okay, so LSTM GRU would enable us to do that. So with that, let me conclude and open the floor for any questions that you might have. Yes, Rajay.
Yeah, Professor, how this sequence to sequence is different from prompt engineering? Because in prompt engineering also, we try to predict the next word or something.
Yeah, so the underlying sequence modeling is more fundamental. It's not limited to RNN, transformers, prompting. So, right? So, sequence, you give a sequence, you want output. That is irrespective of a neural network, that is something that is there, right? So, that's foundational, fundamental. Now, what changes in, say, prompt engineering or here, we know what precisely, at least during the forward pass, if this is the input, this is how the output should evolve. Okay, so that is one way of generating the next sequence. Prompt engineering, imagine for now that you use a different black box. Okay, so, and prompt engineering is also different from what we are doing here in the sense that it is kind of related to our pre-training, right? So, imagine that, okay, in prompt engineering, so your output here in this particular case is 0.25. Now, if you are given an option to correct this neural network, no, your loss is too high, make it a bit more less, right? So that is what you're prompting, right? Now try something else. That is prompting. So that is not what we are trying to do here, right? So it's simply a set of principled equations that we have to determine, to connect the input to the output, and you're learning that through gradient descent. Prompt engineering, you again give a different input. The input changes, right? That is, but the underlying idea that, okay, this, the underlying idea, it is called as autoregressive, which means that there is some connection from past to the next. That is common in all these sequence modeling tasks.
Okay,
Yeah.
thanks. Thanks, Professor.
Okay, so any other questions?
Professor, how prevalent is the usage of RNN in predicting stock prices? Is it a is it, is it one of the things that is used prevalently in industry, or there are some other models which are used for predicting stock prices?
So there is no one size fits all, right? So I know a couple of quant-based companies which use a mix of everything. No, I mean currently none of the companies would bet completely on artificial models, right? But it could be used as a pre-screening, right? So for example, like okay, you would like to make some guess based on what is not obvious, or basically to speed up things, you would get a pre-screened list. And again, there are a few experts looking carefully at those. So that is how it is currently used for any prediction tasks in within the finance sector.
Yeah, because this
The
is like
other,
AR models, autoregressive models, which are which were traditional econometric models, and these are put into
yeah.
your
So
learning stuff.
yes, so what I will tell about that as we progress, yeah, maybe in the next beginning of the next lecture. So there are some advantages over traditional ARMA and AR models
Yeah.
that people use for either sales prediction or stock market prediction, but they can be replaced with that, right? But again, like just with AR model, you would not completely rely on that, right? So that
Yeah,
is,
yeah,
I mean, that is how it is being used in industry, right? And depending on how mature the industry is, uh, the use of newer models would be less. Uh, that is how it is typically done in any industry or any business, right? So if things are working fine, there's no need to change unless there is a demand.
yeah.
So it would that's although there are, like, for example, I mean, that's not just true with finance or any, that's true with any company. If they're making money, then why disturb, right? So
Great. Yeah. Okay.
for example, like in ultrasound, they would use still like a method from um, say 1900s. Also, although there are now newer methods which give you like extremely good resolution images, you still see those hazy pictures in an ultrasound where finding what's going on is extremely difficult. It's not that the technology has evolved, but there is a nice business model in place that is letting them make money. So why change?
Yeah.
That's the yeah. But there are like many of these quant-based are using say RNNs, and it's not mostly for so it is just beyond say stock price prediction, but it is also for credit assessment, fraud detection. There are some low risk propositions that require automation, so that is usually done with neural network models, not precisely answering a question, should I buy this stock or not?
Yeah. Okay. Yeah, that answers, because I agree that AR and these this cannot actually predict. This cannot capture the sort of dynamics that you observe in your stock price movements. It's pretty hard to do that using just these models. So
Right.
I'm just wondering if RNN is actually used in the industry to be, predicting and taking calls on this.
Yeah, it is. Yeah, as I said, like I mean, yes and no. So there are these. Whenever say there is a smaller company, they would use all this. Whenever there's a more mature company, they are hesitant, or there is no need for them to use this.
Right.
That's a more pragmatic answer I would give.
Okay. Yeah. Thank you.
Okay. Okay, so I had this. So is Ram Bahadur still around? Ram Bahadur Adhikari. I did not quite get this question. Okay, Ram. Okay. Okay, so if not, then let's conclude today's lecture and continue next week. Thank you all.
Thank you.
Thanks, Professor.
Thank you, Professor.